Welcome back to Math 1324. We are starting Chapter 6, and the first section is titled The Table Method, an Introduction to the Simplex Method. So a quick introduction. This section will introduce the table method to solve linear programming problems without the necessity of drawing a graph of the feasible region. Remember in the last chapter we solved linear programming problems by graphing the inequalities, finding the feasible region, finding the corner points, and then plugging those corner points into our optimal function. So we're going to solve linear programming problems without doing that process. So the standard maximization problems in standard form. A linear programming problem is said to be a standard maximization problem in standard form if, and here are your three conditions. The objective function has to be maximized. All problem constraints involve less than or equal to and have positive constants to the right of the inequality. And all the variables must be non-negative. So an example, maximize P equals 50x1 plus 80x2, subject to the constraints x1 plus 2x2 less than or equal to 32, 3x1 plus 4x2 less than or equal to 84, and the non-negative constraints x1 and x2 both have to be greater than or equal to 0. Notice that it says maximized. The objective function has to be maximized. The constraints have less than or equal to and positive constants to the right. Less than or equal to 32, less than or equal to 84. And last, all the variables are non-negative. x1 and x2 both have to be greater than or equal to 0. Notice here to the right, I call this the I system. And the I system stands for inequalities. I for inequalities. So that's the I system. Now we're going to talk about slack variables. To adapt a linear programming problem to the matrix methods used in the simplex method, we must convert the problem constraint inequalities. Remember, these were the inequalities up here. We must convert the problem constraint inequalities into a system of linear equations using what we're going to call slack variables. So let me see if I can get them both. Yep, okay. So looking at our problem, do you see how we have x1 plus 2x2 less than or equal to 32? If we want to convert that to an equal sign, we have to introduce what's called a slack variable. So instead of having x1 plus 2x2 less than or equal to 32, I now have x1 plus 2x2 plus some slack variable equals 32. And similarly, instead of having the second inequality, I introduce another slack variable, s2, and turn that inequality into an equal sign. All right, so this was my I system for inequality. This is going to be my new E system for equations. Okay, those variables that were introduced, this S1 and S2, those are called slack variables because each one of them makes up the difference. In other words, it takes up the slack between the left-hand and right-hand sides of the inequality system. So notice if x1 was 20 and x2 was 5, so up here, if this were 20 and x2 were 5, so we'd have 20 plus 30, then s1 would have to be 2 in order to get it to equal 32. Okay, if the decision variables x1 and x2 satisfy the system of constraint inequalities, then those slack variables, S1 and S2 that we just introduced, those have to be non-negative. Okay, let's go talk about the setup of the table method. The solutions of the I system, remember the inequality system? The solutions are the points in the feasible region. Okay, so if we were to graph that inequality system up here, the one circled there in green, if we were to do this using the geometric approach and we graphed the feasible region, all of the points in the feasible region would be solutions to that. So an example, 20, 4. So here's 20, 4. So that point right there is a solution, but 20, 8, which would be up here, would not be a solution. All right, the solutions of the E system, remember when we introduced the slack variables? The solutions of the E system are quadruplets of the form x1, x2, s1, s2. The quadruplets are called the expanded coordinates. For example, 20, 4, 4, 8 and 20, 8, -4, -8 are solutions of the E system. The I system and the E system do not have the same solutions. However, the solutions of the I system correspond to the solutions of the E system, in which the variables x1, x2, s1, and s2 are all non-negative. A solution of the E system in which the values of all decision variables and slack variables are non-negative is called a feasible solution. Again, a solution of the E system where all of the decision variables and slack variables are non-negative, that's called a feasible solution. So looking at some examples, do you see how they're all non-negative? That would be a feasible solution, but this one would not be because of the two negative slack variables. So by looking at line segments that form a boundary for the feasible region, we conclude that for any corner point P of the feasible region, at least two of the variables of x1, x2, s1, and s2 must equal 0 in the expanded coordinates of P. So let's take time to go look at the table method with two decision variables. So here comes the procedure. Assume that a standard maximization problem in standard form has two decision variables, x1 and x2, and M problem constraints. So step 1, we're going to use slack variables S1 through SM, because remember there's M constraints, and we're going to convert the I system with inequalities to an E system with equations. Step 2, form a table with M plus 2 times M plus 1 all over 2 rows, and with M plus 2 columns. And those columns are going to be labeled X1, X2, and then S1 through SM. And that should be the word with. Okay, in the first row on your table, assign 0 to X1 and X2. In the second row, assign 0 to X1 and S1. And you continue until all the rows contain all possible combinations of assigning 2 zeros to the variables. Step 3, complete each row to a solution of the E system if possible. Because two of the variables have the value 0, this involves solving a system of m linear equations in m variables. So you can use the Gauss-Jordan method or any method you find that might be easier. If the system has no solution or infinitely many solutions, don't complete that row. And as we go work through one, this will become hopefully more obvious on what we're doing. Step 4, find the maximum value of P over those completed rows that have no negative values. Remember that the rows cannot have negative values. If the optimal value of the objective function, it is the optimum value of the objective function provided the optimal value exists. Okay, let's go look at an example. With our example from above, you want to maximize P equals 50x1 plus 80x2 subject to those constraints. Okay, looking here, we actually have two constraints. We're not going to count the non-negative inequalities. We've got two constraints. So 2 plus 2 times 2 plus 1 all over 2. We're going to have 6 rows. And then 2 plus 2 is 4 columns. Remember that we have m constraints. And then our number of rows is m plus 2 times m plus 1 all over 2. And then we have m plus 2 columns. That's where we're getting these numbers. 6 rows, 4 columns. Remember the columns go x1, x2, and then starting with our slack variables, s1, s2, s3, so on. Okay, let's go remember what our E system looks like. It has x1 plus x2 plus s1 equals 32. And our second equation is 3x1 plus 4x2. Hold on. x1 plus 2x2 plus s1 equals 32. 3x1 plus 4x2 plus s2 is equal to 84. This is our system that we're trying to solve. Now we're going to use this first row here. If we use the first row, we notice that, let me erase, we're going to plug 0 in for x1 and x2. So our resulting system right here would be S1 equals 32 and S2 equals 84. You can also see that it corresponds to this matrix, 1, 0, 32, 0, 1, 84. Using the second row, okay, hold on. So we see that S1 is 32 and S2 would be 84. All right. Now, using the second row, where, let's go back to our original system, x1, 3x1, 2x2, 4x2. This time, we're going to let x1 be 0 and s1 be 0 in row 2. So I'm going to change x1 to 0 and s1 to 0. Now we have this equation, 2x2 equals 32, 4x2 plus s2 equals 84. So that matrix is here. We get 2, 0, 32. So 2, 0, 32. And we get 4, 1, 84. That's where that system comes from, this matrix. If you go do RREF, that matrix, let's go do that. Let me go open stuff up. All right, here we go on our calculator. Second matrix edit. It's a 2 by 3, and our numbers are 2032, and then 4184. Second quit, second matrix, math, RREF, and then matrix A. We see that our solutions are 16 and 20. So that's where these numbers came from, 16 and 20. And up above, that were here in purple when we solved this one, we got 32 and 84. And we're going to keep solving systems for each row. Okay? When we do that, we're going to solve it 4 more times. When we do that, we notice that we get a negative value here and here. Okay? So solutions in rows 1, 2, 5, and 6 are called basic feasible solutions. And those solutions correspond to the corner points on our feasible region. Remember when we said if we solve and we get negative values for any of them, we ignore those rows? So we've thrown those rows out. So the rows that are left, row 1, 2, 5, and 6, those are called basic feasible solutions. We have a theorem that says if the optimal value of the objective function in a linear programming problem exists, then that value must occur at one or more of the basic feasible solutions. Okay, once we go plug these solutions in, the x1, x2 solutions in, to our objective function, we can see which one gives us the maximum. So this is the biggest value, 1480, of the objective function. So this is our solution to the linear programming problem. Let's go look at a couple of examples. We're going to construct the table of basic solutions and use it to solve the linear programming problem. So here we go. We want to maximize P equals 10x1 plus 25x2, subject to the following constraints. 3x1 plus 2x2 less than or equal to 21, x1 plus 5x2 less than or equal to 20, and x1 and x2 both have to be non-negative, greater than or equal to 0. All right, so we have two variables, x1 and x2. So we know that we're going to have, so m is 2. We're going to have 2 plus 2 times 2 plus 1 all over 2. So 4 times 2 is 8 divided by, 4 times 3 is 12 divided by 2 is 6 rows. And m plus 2, so 2 plus 2 is 4 columns. Let's convert our I system to an E system. 3x1 plus 2x2 plus s1 equals 21. And x1 plus 5x2 plus s2 will equal 20. That's our E system. Okay, our table, 6 rows, 1, 2, 3, 4, 5, 6, 4 columns, and then our objective function. Okay, here we go. If I let x1 and x2 both be 0, then I get, so these are both gone. I will get s1 equals 21, s2 equals 20. And I stop. Now let's go do x1 is 0, s1 is 0. So this time, those are gone. So I get 2, 1, 21, 5, oops, S1 is gone, not S2. 5, 1, 20. If I RREF this, let's go do that. So I get 2, 1, 21. And then I get 5, 1, 20. That doesn't make sense. Hold on. 2, 0, sorry. S1 is gone. There's no S2. 5, 1, 20. All right. I get 10.5, negative 32.5. Okay, those were for x2 and s2. 10.5, negative 32.5. Notice that this is a negative. We're going to totally forget about row 2. All right, let's go do another row. We let x1 be 0, and this time let s2 be 0. So x1 is 0, and s2 is 0. So now I have 2, 1, 21, and 5, 0, 20. And I want to RREF it. All right, here we go. 2, 1, 21. 2, 1, 21. 5, 0, 20. My solutions are 4, 13. All right. So if x1 and s2 are 0, then x2 will be 4 and s1 will be 13. That is a basic feasible solution. Let's go do this again. This time, I'm going to let x2 be 0 and s1 be 0. x2 is gone and s1 is gone. So my system will be 3, 0, 21 and 1, 1, 20. Where am I getting those numbers? They're the numbers here. All right, here we go. 3, 0, 21. And then 1, 1, 20. Seven, 13. 7 for x1, 13 for s2. Okay, 2 more of these things. Here we go. Let's go do, have we done purple? No. Let's do another row of purple. So this time I'm going to have, I have 0, 0, 0, 0, 0, 0. Then I have 0, 0, 0, 0. Then I'm going to have 0, 0. All right, here we go. 0 here for x2 and s2. S2 and x2 are zeros. So I have x2 is gone, and S2 is gone. So I now need to solve 3, 1, 21, and 1, 0, 20. All right, here we go. 3, 1, 21. 1, 0, 20. 20, negative 39. So 20, negative 39. That row is gone because I had a negative 39. Last one. I'm going to do another row of red. All right, this time S1 and S2 are both 0, so those are gone. My system would be 3, 2, 21, 1, 5, 20. If I RREF that one, 3, 2, 21. 1, 5, 20. I get 105013. So my solution, x1 would be 5, x2 would be 3. All right, now let's go kind of clean this up. We said this one was 5, and this one was 3. All right, just a quick recap. Notice that we're not going to use row 2 because we had a negative 32 for S2, and we're not going to use row 5 because we had a negative 39 for S1. Let's go plug in our X1 and X2 and find our optimal solution. I've let 0 be for X1 and 0 for X2. My P is 0. If I let X1 be 0 and X2 be 4, 10 times 0 plus 25 times 4 is 100. Oops, not on that row. Row down. If I let X1 be 7, 10 times 7 is 70, plus 25 times 0, I get 70. And if X1 is 5, 10 times 5 is 50. 50 plus 75 would be 125. My answer, this is the biggest value of P when X1 is 5 and X2 is 3. So again, the answer, P equals 125 is a max, so it's maximized when X1 is 5 and X2 is 3. All right, example number 2, I'm just going to set everything up, and then I'm going to give you the answer, or the table, and you tell me the answer. We want to maximize, subject to, this time we have 3 constraints. So our M will equal 3. Keep that in mind. M is 3. All right, our E system, X1 plus 6X2 plus S1 will equal 72. X1 plus 3X2 plus S2 will equal 45. And 2X1 plus 3X2 plus S3 will equal 72. That is our E system. All right, remember that we have 3 constraints. How many rows will we have? So for the rows, we do 3 plus 2 times 3 plus 1 over 2. So 5 times 4 is 20, divided by 2 is going to be 10. And for columns, we're going to have 3 plus 2, which is 5. 5 columns. So I made my table. There's my 5 columns, 1, 2, 3, 4, 5. And I have 10 rows, 1, 2, 3, 4, 5, 6, 7, 8, 9, and one more made 10. All right, now I get to pick where I put my zeros. There's a method to my madness. X1 and X2 are 0. X1 and S1, X1 and S2, X1 and S3. Then I'll do X2 and S1, S2 and S2, X2 and S3. Then I'm going to do S1 and S2, S1 and S3, and finally S2 and S3. Now I'm going to have to solve 10 different systems. 10 different systems. Ugh. For the first system, I am just looking at this row. All right. It says to make X1 and X2 0. So I no longer have X1s or X2s. My system says S1 is 72, S2 is 45, and S3 is 72. That takes care of the first row. Let's go do it with the second row, and then I'm going to stop. So here comes row 2. This time it tells me to let X1 and S1 be 0. Those are all gone. Those are all gone. What remains? All right, I have 6, 0, 72. Do you see I got the 0? Oh, I've got 2 zeros. 6, 0, 0, 72. And then I have 3, 1, 0, 45. And then I have 3, 0, 1, 72. So let's go solve this system. Here we go. On my calculator. Second matrix. Edit. This is a 3 by 4. First row, 6, 0, 0, 72. 6, 0, 0, 72. The next row, 3, 1, 0, 45. 3, 1, 0, 45. And the last row, 3, 0, 1, 72. 3, 0, 1, 72. My solution is 12, 9, 36. So 12, 9, 36. And you keep doing that way many more times. We're going to do it 8 more times. Now, I'm going to cheat, and I'm going to give you this table filled in. All right. The ones that I'm giving you are going to be here in orange. Row 3 had a 15, negative 18, 27. Row 4 had 24, negative 72, negative 27. 72, negative 27, negative 72. 45, 27, negative 18. 36, 36, 9. 18, 9, 9, 24, 8, -3, 27, 6, 9. All right, remember, so we've done all these systems. We've solved 10 different systems to get all these numbers filled in our table. Now, which ones do we get rid of and not find the P? Anything that has a negative. This row has a negative. I'm not going to find P for that row. This one has negatives. This one has negatives. Yuck. And this one. So I can get rid of 5 rows right off the bat. So our P would be, if x1 and x2 are 0, I'd get P as 0. x1 is 0, but x2 is 12. 50 times 12 is 600. Down here, x1 is 36, x2 is 0, so 40 times 36 is 1440. For this one, I get 18 and 9, so 40 times 18 plus 50 times 9 is 1170. And last but not least, 40 times 27 plus 50 times 6 is 1380. Okay, which one's the biggest? This one? Okay, there's our answer. Our objective function is maximized. The maximum value is 1440, which occurs when x1 is 36 and x2 is 0. Last definition, basic and non-basic variables. This will help us as we move forward. For each row in the table, it's customary to refer to the variables that are assigned a value of 0 as non-basic variables, and to the other variables as basic variables. So if it's assigned a 0, it's called a non-basic variable.